Hello, students. We are going to jump into section 5.2. 5.2 is about multiplication and division of integers, and we kind of start with the idea of modeling it. What is the idea of multiplication of integers? And so when you think about multiplication, and we'll do a couple here. We'll do the chip model, which again is my favorite, the number line model, which is okay. It's not bad. It's reasonable. And then the pattern approach, which, as you've already indicated, if you watched the first video, is not my favorite because of the approach that it takes. So let's go ahead and take a look at this. Chip model can be used to illustrate multiplication of integers. And again, the idea is the first number that you see, positive or negative, and it really doesn't say this here, but I'll add it just because I think it's helpful. First number that is a 3, and the 3 is positive. So positive means that I put in, okay? And then the number is 3, and then we say groups of, okay? So I put in 3 groups of -2. So what you can see is that I actually put in 3 groups of -2, right? Let's see here. So, and again, the reason why I think this is important, and unfortunately it was not stated in the textbook, even though I might have recommended it to the authors, is because the next one, if you had a -3 to start, the -3 starts with a negative. And so the language is not put in, you would think of take out. Okay. So you would take out 3 groups of -2. Now the problem is we always, when we're starting with multiplication, we always start with kind of nothing. We have nothing to start with. So if we say put in 3 groups of -2, well, I could put in 3 groups of -2, perfect, and that would be -6. But when I have to take something out, but I'm starting with nothing, we need to use those 0 pairs. I have to take out 3 groups of -2, and that's what I need to take out. So I need 3 groups of -2, but remember, I have to start with 0. I'm starting with nothing. So if I take out 3 groups of -2, or I'd like to, I have to remember that I need 0 pairs in order to make that work. So right now I start with 0. It's just a really fancy form of 0. And then I find 1 group, 2 group, 3 groups of -2, and I take them out. And then what remains at the end is just 6 positives. So again, some of you have heard the idea that a negative times a negative gives you a positive. This is illustrating why that is the case. Because in a sense, you're removing groups of negatives. And if you remove negatives, it's going to make something more positive. Okay. This is similar, but not exactly the same as if we were doing something like -5 take away -2, which usually looks like a challenging problem. But with the chips, you would start with nothing. And the first thing is, okay, I've got -5, and I take out 2 negatives. Okay, well, here they are. Done. What am I left with? I'm left with 3 negatives, and the problem is done. It's very quick. It's very quick if you're doing it with the chips. So again, if you've struggled with these before, maybe this will actually help you as well, because the goal is that we really understand it well. Number line, multiplication and division. So we always start at 0, similar to the chips. We always start at 0, always face the positive or right direction. If the number is positive, I walk forward. If the number is negative, I walk backwards. And so, for example, 2 times 3 means 2 groups of 3. So I walk 2 groups of 3 forwards. 2 times -3 is 2 groups of -3. So I'm facing forward. Negative number, I walk backwards, but I'm going to walk backwards in 2 groups of 3. So I'm moving backwards, still facing the forward direction. Okay. And then what they do here, this is why this is not my my favorite model. What they say is, hey, be careful. If you get to a problem like -3 times 2, it really creates some problems on our number line. So use the commutative property to rewrite it as 2 times -3, and then you can solve that problem. Which is correct. You can always use these properties. I prefer having a model that uh, I don't have to kind of play games with. So I like the chip model a little bit better. Let's see here. And then the negative times a negative, what they're doing, again, they're playing a little bit of a game because they're saying -3 times -2. So what they're going to do, or -2 times -3, whichever one they had. They had -2 times -3. Let me be consistent so that it matches. They had -2 times -3. So what they did is they said, well, why don't we do 2 groups of 3? And so they did 2 groups of 3, which would be 2 times 3 right over here, right? And then they did, so they started by doing this problem. They did 2 groups of 3, and that's what they illustrate here. Then they said, well, let's do 2 groups of -3. And again, that's listed right here. And now what they're going to say is the number in front, I want to do the opposite of whatever I just did. And that will be the same as the -2 in a sense times -3 because I've gone the opposite of whatever this was. So you get to the end of doing this problem and you find the answer and then you say, but I want the opposite, and that will get me -2 times -3. Okay. So again, you might look at this number line system and be like, yeah, I don't know about that for integers. That requires quite a bit more thinking to use that model. Or you might be thinking, hey, that's a good one to have as a backup. Perhaps a student really enjoyed the number line, like they could move a kitty cat and see it going forwards or backwards. And that's perfectly fine. Lastly, they have the pattern approach for multiplication. And the pattern approach for multiplication is going to turn something into a arithmetic sequence. So when they start doing multiplication, you can see them doing 3 times -2, they get -6. 2 times -2, you get -4. 1 times -2, you get -2. So what they're doing is, if I was struggling to find a -2 times -3, I might use this approach, but I'd start with something the student knows. So this technique most of the time is not covered directly the way they have it shown. Let me illustrate quickly how this would be done in a classroom to make it meaningful to students. Because you're going to be teachers, so we want to see that piece. So here's the idea. Let's say that I want to get students to understand that 3 times -2 is -6. I want to get them here. What I would do is I would start with 3 times 3 and say, we know that's 9, and then ask them 3 times 2. Notice I'm starting with something they already know. I'm starting with positive times a positive. And now we really hit the reach, kind of, we've gone down to where we might kind of be, this is the most that they know. Because the multiplication does continue this way, you could say, well, look at how we got there. What happens? And hopefully you'll connect the idea that you are removing one group of 3. By removing one group of 3, the answer, in this case, the product, will decrease by exactly 3. So if you remove a group of 3 from 0, this now becomes something that they have seen with addition or subtraction. If I have 0, but I take 1 away from it, I would have 3 times -1. And if I remove one group of 3, we know the answer goes down by 3. And so you've got a pattern now that they could use to begin to say, okay, I can see a positive times a negative is equal to a negative. So that's how I would build that up if I wanted them to get to this stage. So once they're comfortable with a positive times a negative equals a negative, and they can kind of see that, then I could go and say, well, let's now do -3 times -2. Okay. But in order to get there, I want to build on what they already know. So this again is a great technique for you as you become a teacher. It's called scaffolding, and it's the idea that I build on what the student knows. So if they know a positive times a negative is equal to a particular number, that's great. Then I would do something like this. I'd say, well, what's 2 times negative 2? What's 1 times negative 2? What's 0 times negative 2? Notice this time I'm keeping the negative 2 constant, because I want to kind of demonstrate that. 2 times negative 2 would be negative 4. 1 times negative 2 would be negative 2. 0 times negative 2 would be 0. This time, what I'm reducing is I'm reducing the number of negative 2's. And what you're doing is when you reduce negatives, tie into this from subtraction. When you pull out or take away negatives, the number goes up because you're removing negatives. Okay. So there we go. And if I keep going with that, then I would have negative 1 times negative 2, which would be positive 2, and negative 2 times negative 2, which would be positive 4, and negative 3 times negative 2, which would be positive 6. And that is how I could get a student to see, using the pattern approach, if all they knew was positive times positive, how I would build and then build a second time. So that's the approach with the pattern one. Unfortunately, the way the book is kind of prefacing it, they don't really show how they got to that stage. They kind of jump into it, assuming that a student already knows a positive times a negative is a negative. I don't think that's quite the case. This one's a little bit more abstract. Okay. So anyway, there's the first 4 products, and there you go. Now they show it with a spreadsheet, which is great. You can always use a spreadsheet to illustrate negative times negative is positive, but they, I guess that's another way to do it. All right, so let's see here, defining integer multiplication. Now, again, those are models. When we try to define it, we want the definition to be free from the models. The models can represent the definition, but they should not be the definition. So definition is, if you have 2 positive numbers, then you end up with a product A times B, because they're just whole numbers, just whole number multiplication. If both of them are negative, then A times B is the product of the absolute values. The product of the absolute values means that each number turns into something that's not negative. And so you have basically converting this back into the answer to this between 2 negative numbers will always be a non-negative number. Could be 0, because we're saying it's okay if one of those numbers is 0. And if one of A or B is less than 0, while the other is greater than 0, then the product A times B is the opposite. That's the opposite symbol out there of these absolute values. In this case, the opposite also does mean a negative, but that's only because the 2 numbers that we're seeing here are absolute values, and they cannot be negative. So a positive times a positive, and then you take the opposite. So this result will be negative, but it is saying if one of them is less than 0, the other is greater than 0. Less than 0 would be a negative. Greater than 0 would be a positive. So a negative times a positive will equal, you guessed it, a negative. All right. Let's move on. So there's kind of the big picture. Properties. These shouldn't be a huge shock to you. They're virtually the same as the properties of multiplication with whole numbers. So they are closed. That means if you multiply 2 integers, you're going to get another integer. Commutative property holds. That means the order can be changed and it won't change the product. Associative property holds. The grouping can be modified and it will not change the product. The identity holds. 1 is an integer, and therefore we have the integer property. And the distributive property of multiplication over addition for integers does work as well, which is pretty cool. And really, technically, this also means you have the distributive property of multiplication over subtraction. I believe they get to that in one of the homework problems. But remember, when we talked about subtraction, if I had A times B minus C, we could simply write that as A times B plus the opposite of C. And now we've turned it into the operation of addition, so the distributive property would work. And then in this section, we're going to see that if you multiply these together, you'll end up with the opposite of AC. And when you do adding the opposite, you end up with, oops, went a little too quick on that, with subtraction. So really, what you can see is that if you start up here, you can distribute across subtraction. But technically, and this is why I said at the beginning of class, there's really only addition and multiplication. We create a subtraction as a way of thinking about those. So very cool. Very cool stuff. And of course, we have the zero property. What we get to see is you multiply by zero, you get zero. Doesn't matter. And now this is a great one that I think, again, some of you might have remembered from a prior class. But basically, if you multiply an integer by -1, you get the opposite of that number. So there is a proof illustrated here. Let's see here. Using this result. Oh, it says using this result. Got it. Okay. It actually doesn't show it. So I have a feeling it's one of the theorems to be proved in this section, but I think it's probably a good one because it ties back into the idea of the additive inverse. So we've got multiplication now tying into the additive inverse. So let's go back and just kind of remember why that's the case. Any number, any integer, I can add its additive inverse, and that gets me to 0. Okay. So if I take that same number and I add -1 times a, what do I get? Well, I'm not sure right now, but let's see if I can simplify. I notice I have an a in both of these, so I could factor the a out. That's the distributive property of multiplication over addition, and that would leave me with this, 1 plus -1. And 1 plus -1, well, those are additive inverses of each other, so this result becomes 0. And the zero property of multiplication says anything times 0 gets you to 0, which is fantastic. So that means a plus -1 times a gets me 0. And a plus the opposite of a gets me to 0. And one thing that we got to see is when you have an additive inverse, if something looks and acts like an additive inverse, that those are unique. And what that means is these two things have to equal each other. So -1 times a must be the same as the opposite of a. And that's the theorem. That's the proof of the theorem and why it holds true. Now you get to use that theorem to kind of say, wait a minute, if I have the opposite of a number, I can turn it into -1. -1 can multiply the way we know how to do, and then I can rewrite it. So you can bring it in and out as needed, which is great to say the opposite of two numbers is always going to equal the product of the two numbers, not opposite. We'll do a few more of those as we go, but there's another theorem that reflects that. And again, this also shows what I just did a moment ago, that why we get the distributive property of multiplication over subtraction. Because you can turn the addition into adding the opposite, and then the opposite kind of comes back together like we're multiplying by -1. Oh, let's see here. So they have simplified this. So a little bit of work from here from your prior algebra classes, perhaps. But this is something I don't think should be that foreign. And we have done something with the difference of squares earlier when we were dealing with some patterns. So again, this is the difference of squares formula, more algebraic. They ask you to do a few practice with it and factoring, and then a barrel problem. Whoop-de-doo. Doop-de-doop-de-doo. Okay, integer division. There we go. All right, so chip model for division. So what we're going to do now is we're going to be kind of making groups. Okay, so this is where things get a little bit challenging with any model, the division involving negatives. So what we're going to do is you can start, and they're going to say partition or divide -15 into 3 groups. You can be splitting that into 3 groups without any trouble at all, right? And then here, you could also think of taking out or subtracting two groups of -5. So this problem over here was -10 divided by 2, if you want to think of it that way. So if I divide it by 2, I can make two groups. I could also do -10 divide by -5, where I'm saying I'm going to take groups of -5 and remove those. Okay, and then we're seeing how many groups can I make? Well, I could make two groups. Over here, if I have -15 and I divide by 3, I can think of making 3 groups. And how much is in each group? Each group has -5 in it. So there's kind of the way that I could do that problem. Okay, so I have a negative divided by a positive, a negative divided by a negative as we were going there. So that's how you can kind of model it. Again, you can do the pattern model for division as well. I would just encourage you to make sure your students know that this does create problems. Here's a couple examples. 3 divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. And therefore, according to this pattern, you would be able to say 0 divided by 0 is 1 if I followed the pattern approach. And this makes Scott very sad because we know that this is actually undefined. So you need to be very, very careful with this. What's the other thing that it could do? Well, I could have done 0 divided by 3, 0 divided by 2, 0 divided by 1, 0 divided by 0. And 0 divided by 3 is 0. Next one, 0. Next one, 0. Oh, well, that means 0 divided by 0 must be 0 because I followed the pattern. And so I think this is where you as a teacher have to really understand the mathematics, because otherwise you could walk yourself right into this and say, yeah, that looks good. But again, unfortunately, this is one that makes Scott sad because 0 divided by 0 is undefined. Remember, this is the one that fails because there's too many possibilities. And it's almost illustrated right here on the screen. Each one of these seems like a perfectly reasonable answer. So why aren't they both answers? And the reason is division has to be unique. And this is not unique. There are multiple possibilities. Okay, and the number line for division, again, I'm not gonna lie, it's not my favorite. But this is number line for division is one that you could use because you're kind of grouping things and figuring out how many groups it would take. It's almost like the missing factor approach. So let's get to the definition, because again, the models are one thing, the definition is the other. And so what do we need? I need to find a divided by b is a integer. Notice it is a unique integer if it exists such that a equals b times c. So we know we check it with multiplication. That's why if you had a problem like 12 divided by -5, you'd say, well, let's see here. 12 is equal to -5 times what integer? And you could try -2, that gets you to 10. You could try -3, that gets you to 15. And you would say, I've got a real problem here. There is no such integer. So 12 divided by -5 is not an integer. Okay. And we could say that it is also undefined. We just want to make sure if we say it's undefined in the integers. There is no integer that makes that happen. Okay, so all of our things that we talked about with whole numbers are still going to be okay. 0 divided by 0 is undefined because it's not unique. 5 divided by 0 is undefined because it doesn't exist. Okay. All right. Let's see here. Be real careful on these parts, E and F, the ones they have as examples here. They are very clearly specifying when you're dividing AB divided by B, you do get A, like you can divide almost, some people say cancel. I want to think of it as removing common factors, but some people do say cancel. You cancel the B off, but just make sure you have to make sure that B is not 0. If B was 0, you'd be looking at 0 divided by 0, which is undefined. So again, very similar pieces here. All right. And ordering integers. So ordering integers greater than or less than, we say to the left of, but basically you can also think of it, if I have to add a positive number to get to the next number, then one is smaller than the other. And that's the definition of less than. So one number is less than another if and only if there exists a positive integer k that you add to the smaller one to get up to the bigger one. Right? And for integers a and b, if one is bigger than the other, if and only if, when I subtract them, I get a positive integer. When I take bigger minus smaller, as you would. Couple of theorems down below here that are pretty nice to know. If you have something that is an inequality, you can add the same number to both sides and it stays an inequality. Okay. However, if you take the opposites, the inequality changes. And this one is really, really helpful. I like this one visually, personally. So if I'm looking over here and I think of the number 0, I think of 4, I think of 6, I would say 4 is less than 6. But now let's take a look at the opposite of 4 and the opposite of 6. So now I'm going to bring those over to the other side. So the opposite of 4 would be here. The opposite of 6 would be here. And all of a sudden, things are different because remember, larger is to the right. So now -4 is actually greater than -6. So if you take opposites, you are changing the inequality sign. Okay. And likewise, the next piece right here is talking about if you want to multiply by something. If you have an inequality, you multiply by a positive number, the inequality stays the same direction. But if you multiply by a negative, the inequality changes. So let's see here. 2 is definitely less than 4. If I multiply both sides by -3, so if n is equal to -3, I would then have -6 on one side and -12 on the other. And -6 to -12, I got to tell you, -6 is actually greater than -12 because it's closer to 0 and they're both negative. You could say it's more to the right on a number line. So that's what's happening with these theorems. They're going over a few things you might remember from prior classes. I hope you do. That if you were solving inequalities back in an algebra class, if you had -3x is less than 6 and you wanted to do something like divide or multiply, you could still do that. You could divide by -3, but what happens is the direction changes. So now you'd say x is actually greater than -2. Okay. That's what we'd be looking at there. If you want to kind of see, well, wait, why is that the case as well? You could say, well, let's start with this one and do something you are good with. -3x is less than 6. You could subtract 6 from both sides, leaving you -3x minus 6 equals 0, and then add 3x to both sides. Oops, not equal to 0, greater than. Add 3x to both sides because that doesn't change anything. And then you end up with this inequality. And here you could divide by 3. And what's great is if you divide by 3, you get that -2 is greater than x, which turns out to be exactly the same thing we said back here. One of them's just a little bit quicker to do. So if you can kind of get used to that, things become a bit easier. All right, let's see here. Okay, so this is a grade 5 with ordering integers. You can kind of see something from the schools you might be teaching in. Use the theorems to solve some inequalities. So you'll be solving inequalities a little bit, and then we get into the homework section. So that really wraps it up for chapter 5. There's not a ton. Be able to look at these problems, and I'll go through a short video on the homework, but be able to look at these problems and kind of see how I could create my own to illustrate what am I doing? What operation am I actually doing? What multiplication or division or something along those lines am I doing? Right? Okay, that's it for now. Off you go.